Recording. There we go. Okay, so ladies and gentlemen, within this model that we built, the agent-based model, one of the salient differences between that model and the system dynamics model was the presence of a network. And that network mediated, it served as the conduit for, it served as a gateway for infection. And within the context of the model, what we had is a network where a given pair of people, A and B, were connected if and only if what condition obtained, what condition applied. They were within a certain range of each other. They were within a certain distance of each other, okay? And we hard-coded that distance to be 75, I think, okay? That leads to a type of network structure. It's called a distance-based network. Local connectivity. Why do I say local? Local in what sense? Space. Yeah, I'm local. I am connected to people local to me in the sense that they're nearby me in space. Now, this is an important distinction because there's going to be another type of network, which we're going to look at right now, which is local in a different sense. It's local in terms of a natural ordering of the different agents. So instead of being in space, it's locality in terms of a linear ordering of the different agents. So I'd like to go and take that model that we've built, and I'm going to load it in again. Here we are. Mumble. Oh, wow, look at that. Okay, it was a really unhappy camper. So models built in class, hybrid, let's try that again. Okay. So we're going to set the network type to be, instead of a distance-based network, here we are, we're going to set it to be a type of network called a ring lattice. Okay? So to do this, go to main and scroll down in main to this area called space and network. And in space and network, you notice that you can set the network type. And I'd like you to change it to be ring lattice instead of a distance-based. And you'll notice with ring lattice, we have a different choice. We have a choice as to how many agents each agent is connected. So here, every agent, the agents are going to be conceptually arranged in a modulo type structure, in the sense that it's almost linear, except the last one is going to wrap around to be connected with the first. So you can imagine agents in a ring, and each agent is going to be connected to the neighbors in that ring. It's a one-dimensional structure locally. What I mean by that is it may appear in 2D space, but you're logically connected to those in some ordered way on either side of you. And this is going to lead to a different dynamics. Now, I would ask you, ladies and gentlemen, to bear with this for a little bit. I'm going to run this with the baseline simulation here. Here we go. 2 connections per agent. And I'd like to run this baseline. How do you expect the situation to be different? Same model dynamics in terms of its characterization. How, if anything, do you expect it to be different? Anyone? Okay, well, the ordering is not clear, right? You've got all these lines around. You notice to how many people is each person connected? 2 people. And they're logically connected to a person left and right, but it's not obvious. So, ladies and gentlemen, I'd like to go do something. So go to main, and in main, go down to the space and network area, and I'd like to set it so the layout type is set to be ring. What that's going to mean is, remember, now, since we have a logical network that doesn't care about geometry, inherently, this is just going to be a convenience visualization measure. This is not going to, because we set them in a ring, it's not going to directly, the layout type, it's not going to directly affect to whom they're connected. just going to affect what they look like geometrically. So we're going to run this. And not surprisingly, what do you think we'll see? There we are. Okay, so what's going to happen? How is this changing the dynamics of the network? Whoa, what's that? Okay, let's try that again. Even more spatially localized. Okay, so let's try this again. Can anyone see some differences in these graphs that can be explained by differences in how it's propagating along this ring? What's different from what it was before? Why is it always seem at such low levels and then to die out so readily? What's going on?
Because of the connection between the regions.
Yeah.
And since it's a small network,
Okay.
like small connection, that's
Yep.
why the prevalence
Okay.
of the disease is low.
Okay, so it's a bottleneck, right? It's a very constrained mode of propagation. In order for it to propagate along this network, across this network, what has to happen? If this guy down here is ultimately going to affect this lady up here, how does the infection have to go? It has to affect everyone in between. If one person in between is stubborn or is recovered early and doesn't doesn't let the infection pass, it's going to die out, right? Very localized, very constrained, very limited in how it can spread. Now, you could vary some parameters here. Instead of having them, and you could argue, well, maybe they shouldn't be constrained to have 2 people on average. So at least give them 4 connections per agent. So I'm connected now to not just the people on either side of me, but the people 2 over as well. Okay, how do you think that will affect things? Anyone? Yeah, so it might make it a little bit more resilient in terms of not dying out, but it's still going to be ultimately pretty darn constrained to before. You'll notice, it's starting down here and it's not getting very far. Just as a sanity check, I'm using a fixed seed, so I'm going to change it to a random seed here. Here I am, and I'm going to run it. Boom. Okay, it sort of spread over a portion of the network. It moved over. It's moving in a very linear way, you notice. That's all it can do. It moves kind of along the network. Pretty darn constrained, even more so than the 2D space. At least the 2D we can move in the X and Y directions. Now we can only move in one. Well, two directions along this one-dimensional torus, this one-dimensional, should say, ring. Okay, ladies and gentlemen, a ring lattice network. Extreme locality. Okay? Extreme locality here. Even more so than a 2D network. 2D network is also pretty constrained. You're spreading to your neighbors in space. Pretty local, but at least there's more degrees of freedom. Ladies and gentlemen, I'd like to go to the opposite type now. But before that, I'd like to put something else in this model. Ladies and gentlemen, this model has got a great view over time, but what is it missing in terms of cherished depictions, at least cherished to your professor? What other depiction could we give of model state besides state over time? What other ways do we have of characterizing graphically the model state? It's a plot. A state space plot, indeed. Okay. So, ladies and gentlemen, I'd like you to go to Analysis, and I'd like you to go drag in a plot. Okay? Here we go. Okay. There we go. Okay. And let's call this SI state space plot. Doesn't leave a lot to the imagination. Okay? So it's going to display S and I. The data here is going to be for the first one, we're going to have it be for the aggregate model. And the X value will be given by what? Anyone? Susceptible. And the Y value will give it by infective. Okay. Now this plot is not going to totally characterize the state because we're not specifying exposed, for example. But it's going to give a partial sense of it. Okay. And now we're going to add another one. And this is going to be ABM. And the X value here will be given by something we need to create. Right? We have over here in population, we have a count infective. What do we still need? A count what? Count susceptible. Over here in population. Count susceptible, and heck, it's going to be very similar to this. I wish there were a way to abstract it, but alas, we're dealing with the tyranny of AnyLogic. So we can't actually, we don't have that option to kind of abstract it away from that. So this is person.susceptible. AnyLogic has great flexibility in many things, but its statistics needs a little bit of overhauling. Okay, item.instate person.susceptible. This is going to be the count of susceptibles. Okay, that goes in the population here, just like count infective, count susceptibles. Only difference is this instead of person.infective. Great, ladies and gentlemen, here we go. Okay, so we're going back to this plot, and the x-axis value will be what? How do I get the count of susceptible from the population? Anyone? Yeah, population dot count susceptible, right? Good. Okay. And suppose now I want to get the count of infectives. Here I can do this. Dot count infective. Okay. So, ladies and gentlemen, we have that. We'd like it to update the data automatically, sure. And we're going to keep up to 1,000 latest samples. Remind me, were we running this to time 1,000 or 2,000? 1,000. Okay, good. Okay, great, ladies and gentlemen. Okay, now for the vertical and horizontal scale, we're doing counts here, and I think we'll let them scale themselves for now. Okay, so here we go. Let's see what this engenders here. Okay. So here we have a state space plot. ABM is this red one, and the aggregate model is this one here. What's going on with the aggregate model? Where is it right now? It's here. It reached an equilibrium. It sort of went up. Where did the agent-based model go? Well, it didn't go very far. Let's try running it again. I set it to use a random number seed. Basically, it's a similar deal. It's kind of way down here. Ladies and gentlemen, rather different. Okay, let's go. Let's keep our focus, though, on the networks. Let's go to main. This is you with two connections on either side. Next, I'd like to do an entirely different sort of network. Ladies and gentlemen, we've been dealing with two types of networks. To wit, distance-based in 2D, ring lattice 1D, that are very localized. A random network, by contrast, has any two pair of people, A and B, connected with equal probability. No matter where they are in space, no matter what their number is, person 1, person 2, person 3, they're not localized at all. In fact, it's the opposite of localized. It's entirely global. It doesn't care about who, it has no preference to whom you're connected. Any two pair of people are equally likely to be connected. How do you think this dynamics will vary? Let's focus on this baseline case, the normal simulation, population 250. How do you think this will vary compared to the aggregate model? Anyone? What do you think will happen now? How about a prognostication from the audience?
It'll be pretty similar. We don't have that space.
Yeah, so much more similar. Andrew hit it on the head. Now, did it go to the same equilibrium? What happened there? So let's run that again. This is again. Make sure you set it so that your random seed is different every time. What's going on here? What's going on? It's kind of got an orbit around a sort of equilibrium too, right? Look at that. It's kind of looping around. You can kind of see it, right? It's looping around this area of space in this kind of semi-stochastic way, in the stochastic way. There's some order there, but it's looping around. You could see it in state space, okay? Run it once more. Here we go. The deterministic model is very clear about its preferences. What happened this time? It just died out up front. It didn't even take off. How about now? Didn't even take off. How about now? Let's try it. Try this. Didn't take off again. Okay? Took off in a big way. Okay? Here we go. So ladies and gentlemen, when it takes off, it's a lot more similar to the aggregate model, but there's still the chance it will never take off. After all, that period where it starts with one person infected is a very vulnerable period. All right? Okay. So that's good. Now, if we were to go up to a population of 1,000, let's say, do this with a population of 1,000 and run it there, how do you think this will differ from the aggregate model? Anyone? Anyone? What similarity do they have and what difference?
They initially follow the same path.
Initially, they follow a pretty similar path. Other similarities? Well, they both go towards and kind of loop around to equilibrium. Now, the aggregate model kind of goes up and comes and reaches equilibrium here pretty quickly. It kind of goes and it loops and it settles in there. This one here sort of goes around, but ultimately it's going around an equilibrium that's not so far off from this. I mean, it's not immediately next to it, but it's not immediately far off. What do you think would happen, ladies and gentlemen, if we were to increase the number of connections that each of those agents have? So let's go to main. Let's go down main. And here we have connections per agent 4. Let's suppose we made it connections per agent 10. What do you think the difference would be? How would that change things, if at all?
It'll be closer to the aggregate model.
And why is that? Good. I like your answer. Appreciate your thinking about it. Why is it closer? Will it prevent the early extinction issue?
Probably.
It will help a little bit, right? Because they're connected with a bunch more people. What are we seeing now? Well, it's not exactly the same, that's for sure. But is it going to a somewhat similar equilibrium? Yeah, I mean, it's looping around it, all right? Okay, try that again, all right? So that's with 10 connections per agent. Ladies and gentlemen, think about an infected person for the aggregate model. So each unit time they can mix with a certain number of people. What's our contact rate in this model again? 1 per day? 1 per day. So each day they mix with 1. In an aggregate model, who are they mixing with? Is it the same person every time? Anyone. It's anyone in the entire population. And that's a little bit like what this represents, except here with a random network, you're connected with particular people. These are 10 particular people to whom you're connected. But they're all across the network, in contrast to a ring lattice network. Ladies and gentlemen, let's go try this. Let's go try this instead of just 10 people. Let's have each person connected to 20. What do you think the change will be yet? By the way, this is bad form. I'm just hard coding this in the interests of time. It would be nicer if we were to encode it as a parameter, but we're trying to explore many types of networks, so I don't want to get too caught up in this. Okay, here they're connected to 20 people. What are we seeing in terms of dynamics? Well, once again, I mean, it follows pretty darn closely here, and it's going to an equilibrium that seems very, very close indeed to the equilibrium seen for the other model. You could again see it here. Very, very, very close, circling around. So, and it's getting seemingly tighter over time. Okay, so running that again. It's another interesting phenomenon, and one for which I don't have a ready, immediate explanation. It's an observation. Ladies and gentlemen, you notice as it runs, it loops in closer. Look at the initial swings here, right? Initial swings in terms of fraction infected. It goes way down, goes up, goes down. But as time goes on, you notice that it's kind of not quite as far out often. They're often somewhat smaller oscillations here. But it can kind of go in these phases between sort of more pronounced and less pronounced. So I'm hesitant to give it much specifics. We'd also want to stop changing the axis here, scale. Anyway, random network. If we were to change it one more time, so each person is connected with 40 other individuals, right? As you might expect, it's going to get closer and closer to what we call random mixing. Each person is just going to be mixing with a broad set of people, and it's not going to be a particularly privileged set. They're mixing now with 40 people, and you're going to see it be much more similar to what we see with this case. It's going to an equilibrium that's much more similar. Okay, ladies and gentlemen. So a random network has no locality. It has no preference for connecting people that are similar in space or similar in position in the set of all people in the population. But let's explore a few other types of networks. This next one that we're going to explore, ladies and gentlemen, we go to main, we go down main to space and network, and I'd like to go to network type, and I'd like to pull down small world. This type of network, mark my words, this type of network will be a combination of the two last extremes. On the one hand, locality, extreme locality, on the other hand, extreme globalness. And this will be almost a linear combination of them, the network itself. That doesn't mean the results of it will be a linear combination of the results of each of those. But take a look at this. I'm going to go down again to 4 connections per agent. And you notice there's this thing called neighbor link fraction. You notice when I set network type, the choices associated with that vary as well. Here it's going to be neighborhood link fraction 0.95. So what that's going to mean is that 95% of the time I'm going to be connected with a neighbor in a ring lattice network. Each person is going to be conceptually in a ring lattice network. 95% of their connections are with others who are neighbors to them. But, ladies and gentlemen, 5% of their connections are going to be with people across the network. What do you think the dynamics of infection spread in this network is going to be like? Will it be more like ring lattice? More like a random network?
It'll be more like ring lattice because the relationships between the people are closer together, except for the 5% one. So
Okay.
it'll have like a chance to spread, more of a chance to spread than ring lattice would.
Mm-hmm.
But in general, since they're so close together, it won't be much different than ring lattice.
Okay, so here we do see it spreading. You notice most of the people are arranged in this network. Well, they're all arranged in a ring, and they are connected with neighbors in the ring. But you'll notice what just happened there. What just happened, ladies and gentlemen? Sorry?
It's spread across
It spread across the network. And how did it leap across the network?
with one of those 5.
Yeah, by one of those global connections. Okay, now this spark, which started here, which in a ring lattice, pure ring lattice network, had to spread locally. Now it's spread, it jumps, right? It sends sparks across the network, across these connections. Do you see that? Do you see that? It's jumped across the network. So, ladies and gentlemen, take a look at the network dynamics here. Is this the same as ring lattice? What was ring lattice like? Anyone remember?
Just died out.
It tended to die out at really small levels. Now, in this case, is this network yielding results very, very similar to ring lattice? Not really. Is it giving results that are the same as the aggregate network? Not really. It's sort of biased off of that. But it's very different at the same time from ring lattice. Let's try it again, right? Here we go. Try it again. Okay. I'm going to turn off the really high speed here. Okay. And the point is, you can now jump across the network. Those small number of connections make that occur across the network. Just a small number can make a really disproportionate difference in the dynamics of the network. So we end up getting an equilibrium that's rather different than the one that we got with an aggregate network. These are smaller numbers. But ladies and gentlemen, it is something which is also very different from a ring lattice. Even though it's a mixture, even though it's mostly ring lattice in a structural sense, even though we only had a very small density of these sort of global connections, that small number of global connections made all the difference because they allowed the infection to spread from one area to the other. Okay, it can still die out easily, but we do get this kind of dynamics, which is more similar to what we get with a random network than with a purely ring lattice. Just those small number of connections. Ladies and gentlemen, a small world network. Now that notion of a small world network, the very name of it, is designed to communicate one of its sort of the big themes behind it. You know, there's a lot of connections we have in life which are with nearby people. We see our family day to day, or we see friends day to day. We're mixing with a lot of the same people. But then we tend to have a small number of connections that are with people from long distances that we have. And those connections can sometimes make a big difference. The example that's sometimes used from this, which many of you will have heard of, is the idea that if you think about the world as a whole, we're knit together with a surprisingly small number of connections. surprisingly small number of connections that it would take for me to be connected with someone in Malawi. Most of our connections are local, just a few global, but those few global connections make a great deal of difference in terms of outcomes. Okay, in terms of outcomes, in terms of dynamics. I'd like to show you one final type of network, and then there's going to be a take-home exercise, which I will aspire to release by tomorrow, which will let you explore a little bit some of the additional properties here. Okay. So the additional type of network is one called a scale-free network. Okay. Scale-free network is going to be one we're going to be talking about quite a bit next time. And a scale-free network exhibits what's called a heavy tail, meaning most people have few connections, but there's going to be some people with a huge number of connections. And they're going to end up distorting the dynamics in a big way. They're going to be the tail that wags the dog. Okay? They're going to be the small number that disproportionately affect the network dynamics. Now it's kind of hard to see here, so I'm gonna down the number of connections per person here a little bit. But here you see a sort of dynamics associated with that. Okay, ladies and gentlemen, I am going to go to main, and I've got my eye on the clock here. I'm going to bring down M here to be 4. Okay. And next time I'll see if I could talk about the M parameter and its meaning here. Okay. And what you'll notice is that here we have individuals here who have a large number of connections. Other individuals will tend to have a smaller number of connections, okay? But there's going to be a certain number of individuals who have a very, very large number of connections. And what you're going to see is that in terms of the dynamics here, we're going to see a situation where often it will stay resident, and it will stay resident particularly because of these individuals who have a large number of connections. So suppose you're one of those individuals with a large number of connections. Can anyone give an intuition for why those individuals may have disproportionate impact, disproportionate level of influence on the level of infection in the network? Why is it that these small number of individuals with a large number of connections may be disproportionately influential?
Well, if the system is normally constrained by locality and space, then any element in the model which ruptures that locality is going to have a big impact.
Okay, so here, these individuals are connected with large numbers of people. So what do you think, if you're connected with a large number of people, how is that going to impact the risk for you to get infected?
There's a larger risk for you.
Yeah, you're like a magnet for infections, right? You could get it from any of the 50 people to whom you're connected, right? Okay, suppose that you're one of those people and you get infected. How does that affect the risk to others?
Greatly, because if they're connected to someone with a large number of people, then that person has a large number of people to infect.
Okay, that's true. And you can disseminate to a lot yourself. And chances are that some of their connections with other people with a large number can easily get infected again. The point is that those people are both more likely to get infected and they're more likely to pass on the infection because they have lots of connections. So you'll notice that this infection is sticking around for a very long time. It has this sort of doggedness to it. See that? Where it's really, really sticking around. It's not dying out easily here. Not dying out. In contrast, even to that first situation where it did die out often, after a little bit of running. Here we have the infection, and it will often stay quite at high levels in this group with high numbers of connections. Ladies and gentlemen, you're going to explore for your next take-home exercise the relationship between the number of connections a given person has and the network type. You'll see that there's very different histograms associated with people's number of connections, different distributions associated with the number of connections, depending if it's a scale-free network, a small world, a ring lattice. Secondly, you're going to look at the relationship between their number of connections on the one hand and the number of times that they're infected, okay, as a scatter plot, looking at where the X location will be the number of times, number of connections they have, the Y location will be the number of times they've been infected. Okay, so we're going to do that atop this same model. But one of the big messages here, on which I'm closing, is that networks matter for dynamics. Ring lattice network, easy die out of infection. A totally global network, the Poisson random network, also called Bernoulli random network or Erdos random network, the infection spread is often more similar, particularly as you increase the number of connections per person. It's much more similar to what you see with a random mixing model, with one of these aggregate models. A small world network, just those few connections can have a disproportionate impact in how it spreads. It takes it out of the regime of almost always dying out like in a ring lattice and gets it much more towards the random network. A scale-free network, persistence of infection in individuals who are at high risk because they attract the infection and they disseminate, and those individuals are those with high number of connections. Next time we're going to be exploring this a little bit more, talk about your take-home exercise, and talk about ring lattice networks, about scale-free networks in particular. And one of the reasons they're called scale-free, because their structure is independent of scale. There's that aspect of the structure that's independent of scale. And it turns out that scale-free networks have been identified within a huge number of human-created and natural systems. The structure of the internet, the patterns of connections between companies or between individuals, the contact patterns. It turns out that a lot of features in the world exhibit this scale-free property. And we'll investigate that on Tuesday. Okay? That's all for today. Thank you very much. Again, that comment that on problem set 2, you will want that for problem 3, part A. You will want to run it for that value of beta. And that's important to be able to compare it in the later part of that problem. Okay, thank you very much, and I will repair to office hours now.